Welcome everyone. Today we're going to be looking at my personal favorite integration technique, substitution rule. And we're going to particularly look at it in the context of indefinite integrals. So this is a good one. So the first kind of thing we'll discuss is that we've been kind of through Calc 1, we've learned a whole bunch of derivative rules and derivative techniques. And at the end of Calc 1, we just started looking at some integration techniques. And for the most part, each derivative rule that we learned sort of has a counterpart integration technique. So for instance, we saw for the sum of two functions, how would we differentiate that? Well, we would differentiate the first function, differentiate the second function, and then add them together. Integration worked very similar. There was a very similar integration rule that said if we wanted to do the antiderivative of the sum, well, we would do the integration of the first function, the integration of the second function, and then add them together. And we saw similar rules for subtraction. So if we were doing the derivative or integral of a function subtracted from another function, very similar context. If we had a function being multiplied by a constant, there were very similar rules for derivatives and for integration. Now, one of the big derivative rules that we learned was chain rule. And this told us how to differentiate the composition of two functions. So that's the context we used for chain rule. And we use some terminology here that's going to carry over into this next section where we talk about substitution rule. And the terminology was we called we had the outer function. So in this formula here, our outer function is f. And then we also have an inner function. So what does the chain rule actually say? Well, it's a derivative rule that says if we wanted to do the derivative of f of g of x, where g of x is the inner function, well, how would we differentiate that? We would differentiate the outer function, keep the inner function the same, and then multiply by the derivative of the inner function. And that's what we're seeing on the right side there. It's the derivative of the outer times the derivative of the inner. So that's the chain rule. And what we're going to learn in this section with substitution rule is we're going to learn the integration counterpart, the integration rule that basically reverses or undoes what the chain rule is doing. And so we're going to be talking about inner functions a whole bunch here because that's really going to be the important way, or that's going to be the way we kind of get started with our substitution rule. So it's always important to keep this derivative rule in mind because this is really what we're going to be undoing when we talk about substitution rule. We're going to be undoing the chain rule. So we always want to keep in mind, what is the outer function? What is the inner function? So let's actually read through what the substitution rule says. It says if u equal to g of x is a differentiable function and f is continuous, then the integral of f of g of x times g prime of x is equal to the integral of f of u du. Now, that's the formula. And the way we're going to actually approach the substitution rule is we're going to think of it more as a process. So you could memorize this formula if you want, but we're going to think of it more as a process. And the first step of that process is to choose u and calculate du. And how we choose u really comes from us being able to pick out what the inner function is. So when we say u is equal to g of x, really we're looking at our function and we're identifying what the inner function is. And that's what we're seeing right here. G of x is inside that function f. And so we normally are going to say, all right, we're going to let, in step 1 of our process here, we're going to let u equal to g of x. We're going to let u equal our inner function, so that when we replace it, we're going to kind of substitute in that value for u. So instead of talking about f of g of x, we're going to be talking about f of u. And then same thing, once we calculate u, once we pick u, we're going to calculate du. And so this is the differential du, and the way we calculate it is let me use a different color here. And how we're going to calculate it is we're going to do the derivative of g and then multiply by dx. And so if we look up in our integral our complicated integral there on the left that we're trying to simplify, we see g prime dx right on the end here. And that's going to become our du. So substitution rule, basically we choose u, we have to identify our inner function, we calculate du, and then we put those pieces into our integral, and it simplifies it down. It simplifies it. So if we look at this formula, the integral on the left is this complicated thing, f of g of x times g prime of x. It's going to be this complicated integral that we really don't know how to handle. And once we go through the process here, we're going to have an integration problem there on the right that's going to be a whole bunch easier to do. So it'll be the integral of just f of u du, and we're only going to have u variables there. So that's really how this process is going to work. Step 1, identify the inner function. That's us choosing u, and then we calculate du. Step 2, we're going to substitute those values into our integral. And that gives us an easier integral. So step 3 then is to just integrate that new integral, which is now all in terms of u. And then finally for step 4, once we have our antiderivative, it'll be an antiderivative in terms of u. We can just convert it back to our original variable, and we're done. So we'll see how this process works in a few examples, but it's good to just outline it here. But one key thing that we're going to have to remember is that in step 2, where we're substituting in we're substituting in u and du, we need to convert all instances of that original variable. So wherever we see an x, it needs to become something involving u. Wherever we see dx, it needs to become something involving u or du. So we need to convert everything. All the x's that we see in some way have to be converted into something involving u. And we need to do that before we move on to step 3. So once we get to step 3, which is actually just doing this integral here, once we get to step 3, which is just doing that integral, there shouldn't be any x's anymore. It should all now be our new variable u. All right, so again, just a reminder about this. We're going to be paying particular attention to the differentials at the end. So this is kind of an important part of how we do substitution rule. Once we choose u, we calculate du, and we do this by, if we set u equal to a function g of x, how do we calculate du? Well, we differentiate g, and then we multiply by dx. So that's really the process here. How do we calculate du? We do the derivative of u, we do the derivative of g, and then we just multiply by a dx. And that's exactly what we're seeing here. That's how we do this. So it's going to be important to remember the dx and the du's. We're going to be paying attention to those as we go through our examples. So let's try example 1. We're going to look at the integral of 3x plus 4 raised to the power 10 times 3. And we're going to see how to do this involving substitution rule. And really the reason why we would need substitution rule is this isn't one of our elementary form integrals. It's not one of our basic integrals that we can just do. There's a little bit more going on here. So let's see how the process works. So we're going to do example 1. So the integral of 3x plus 4 raised to the power 10 times 3. And we're going to evaluate this indefinite integral. All right. So what's the first step? Well, the first step is we want to pick u. And how we do this is we look for the inner function. So if we're looking at this integral, we see parentheses, 3x plus 4. Inside those parentheses, that's our inner function. So our inner function is going to be 3x plus 4. It's inside the parentheses that we see. It's inside that power function raised to the power 10. Once we pick u, then we calculate du. So we're going to start by differentiating 3x plus 4. Derivative of 3x plus 4 is just 3, and we multiply by dx. All right, so we've done the first step. We've picked u, we've calculated du. Now we're going to move on to step 2, and this is where we take those two pieces and actually plug them into our integral. So let's see what's going to happen here. Well, we have this 3x plus 4 inside the parentheses. We know that's going to become 10, or become u. And then we have this 3 dx here at the end. And if we look, we know exactly what 3 dx is going to become. It's going to become our differential du. So if we put those two pieces in, we're starting off with the integral of 3x plus 4 raised to the power 10 times 3 dx. And we're going to replace that 3x plus 4 with a u. So we're going to get the integral of u to the power 10. And then that 3 dx there, that's going to become our new differential du. So we take this complicated integral there on the left, and we have now this easier integral, the integral of u to the power 10 du on the right. And that's step 2. It's just to convert everything, put all the pieces in. And if we notice that integral now, that new integral, there's no x's, all the x's are gone, and all we have left are the new variable, the u and the du. All right, so now that we have our integral all in terms of u, now we can go on and do the integration. So step 3 is to do the integration, and this is just power rule. So let's do power rule. We're integrating u to the power 10. So our variable is u. We add 1 to the exponent, so that bumps us up to 11. Take that new exponent, flip it, put it in front. So we get 1 over 11 in front. And we just did the integration, so plus c there at the end. And that's step 3. Do the integration. So you don't want to forget, that's the whole thing we're doing here, is we want to do the antiderivative. So at some point you have to do an antiderivative. And then once we have that, the last step, step 4, is to convert back to the original variable. So we're going to convert back, and wherever we see a u, I see one right here, wherever we see a u, we're going to replace that with 3x plus 4. So we end up with 1 over 11 times 3x plus 4 raised to the power 11, and then our arbitrary constant there, plus c at the end. And that's really step 4 of the integration substitution rule process here. Step 1, choose u and calculate du. Step 2, put all the pieces in so that we have an integral all in terms of u. Step 3, actually do some kind of integration, do the antiderivative. And then step 4, once you have the antiderivative, convert back to the original variable. So really that's the process. Now, you might be wondering, why did we pick u there? And it really comes down to being able to identify the inner function. So, and this is going to be a recurring theme when we talk about substitution rule, is how do we actually choose u? And it's not always clear cut. There's not always a clear cut answer how we pick it. So, it takes a little practice. Sometimes you might pick a u value and it just doesn't work out and you need to try something different. So it's a little bit of trial and error as well. And that's okay. But the process we're going to be kind of taking most of the time is to kind of break our function down into two pieces. And invariably it'll be a complicated piece and then just a less complicated piece, something that's a little bit easier. And really where we're going to focus when we're trying to decide what u should be is on that complicated piece. So, for an example, as an example, in example 1 there, we were doing the integral of 3x plus 4 raised to the power 10 times 3 dx. That was what we did in example 1. And if we break that function apart, there's really kind of two pieces that jump out at you. There's the 3x plus 4 raised to the power 10, and then there's this 3 that's next to the dx. So there's really two pieces that we have going on here. There's a complicated piece, 3x plus 4 raised to the power 10, and a less complicated piece, the 3. And what we're going to do is we're going to identify the inner function in that complicated piece. So for this example, we had 3x plus 4 raised to the power 10. The inner function was literally what's inside the parentheses. And that's why we picked u equal to 3x plus 4. It's inside that raised to the power 10 function. And so this is what we're kind of looking for, is we identify the complicated piece, and it might be in the form of something raised to the power n. So we have a nice big set of parentheses and something complicated looking inside the parentheses. That's what we're going to pick for u. We're going to let u equal what's inside the parentheses there. And the reason is once we convert that over, it'll be something a lot easier. It'll just be u to the power n. And we know we can just use basic power rule for integrating u to the power n. If we look at our complicated piece and we see a fraction, so 1 over, and we have a complicated denominator, well then usually we're letting u equal what the terms are that are inside the denominator. And why do we do that? Well, we have another basic form, which is our integral of 1 over u. And we know that's equal to the natural log of absolute value u. And really that's kind of a special case. So I should be a little more careful here when we talk about power rule. Power rule only works if n does not equal -1. If n is equal to -1, well then we're actually in this case here. So this is almost like a kind of a special case of the power rule when n is equal to -1. Behaves differently. Integral of 1 over u is the natural log of absolute value u. So if we see a fraction, maybe let u equal what's in the denominator. If we see an exponential function, so e, and then we have some complicated terms up in the exponent, well, maybe let u equal the terms that are inside the exponent there. And again, that comes down to the fact that we know how to integrate just e to the u. It's e to the u. The same goes for maybe trig functions. So maybe we have sine or cosine, and then we have a whole bunch of complicated terms inside the sine or the cosine. Well, we're looking for the inner function, so we would let u equal those terms inside, again, the parentheses. So, you're looking for the inner function, and a lot of times if you see parentheses, that's a giveaway that there's an inner function. So let's try another one of these. Let's try example 2, and we'll keep what we just talked about in mind. So we have the integral of 2x e to the x squared. This is what we want to do. And we know the process. We need to choose u, calculate du, and so on. But first we need to figure out, how are we going to pick u? So let's start by just, and this isn't necessary, but it can be helpful, especially for more complicated integrals, is to just write down the two different pieces of your function. So we're just thinking about this. We're kind of, this is the behind the scenes work. This is kind of what we're thinking in our head. So let's write down the two pieces. So I might break this apart and say, okay, I have a 2x. And then separately, I also have this e to the x squared. Those are the two pieces of my function. And I want to focus in on the complicated piece. And I would think e to the x squared is a whole bunch more complicated than the 2x. So I would focus my attention on this e to the x squared. And I see that we have e raised to something complicated. E raised to an x squared. There's more than just an x there. And we see that we're really in this case here where we have e raised to something else, to the x squared. And what we should do in that case, again, maybe this works, maybe it doesn't work. It's going to work, but sometimes when we're doing these, you might pick a u and it doesn't work, and that's okay. But what we'll pick here is we're going to let u equal the terms that are inside the exponent. So we're going to let u equal x squared. And again, that's because x squared is in the exponential function. It's the inner function there. All right, so let's write this out formally. So example 2. We're doing this one for real now. Integral of 2x e to the x squared dx. We've identified our complicated piece. It's the exponential part, e to the x squared. And step 1, we're saying we're going to let u equal the term that's in the exponent, x squared. Then the second part of that is to calculate du. So we're just going to do the derivative of x squared. It's 2x. And then part of this is multiplying on dx there. So we've chosen u to be x squared. We've calculated du to be 2x dx. And that's the first step. So the second part of this is to fit those pieces in to our integral. We want to convert all the x's into u's. And it can be helpful, again, not necessary, but to move the pieces around. So it's sometimes helpful to take that complicated piece of our function, in this case the e to the x squared, put it first. And then move all the other terms and put those next to the dx. Still inside the integral, but just put them next to the dx there. And what we do in step 2 is we want to convert all those x's into u terms. And we have our two gadgets here to work with. So we know that wherever we see an x squared in our original integral, we're going to change that to a u. So right here, that x squared, by design, that's going to become u. So that's good. Let's start writing this out here. So it's going to become the integral of e to the u. Now, what's going to happen with this 2x dx? Well, we know what 2x dx is. We know that from right here. We know 2x dx is equal to du. So we're going to get the integral of e to the u du. And what we've done essentially is we've taken an integral that, we really had no idea of how to do, 2x e to the x squared dx. It was complicated looking. And with this substitution, we've produced an integral that is a whole bunch easier, the integral of e to the u du. That's something we can do. So that's step 3, is just do that integral. So what's the integral of e to the u? E to the u. And then we put our arbitrary constant on at the end, plus c. All right, so that's looking pretty good. Now, the only thing that's left to do is convert back to the original variable. So that's step 4. We want to get back to x. So right now our antiderivative is in terms of u. Wherever I see a u here, I'm just going to convert that back with what I know u is equal to. It's x squared. So it'll be e to the x squared plus c. And so now that's my answer. That's my antiderivative back in terms of x. All right, let's try one more of these. Helps to practice. So substitution rule really comes down to just practice, practice, practice. All right, so example 3. We're going to do the integral of 3x squared over x cubed plus 1. And again, it's helpful to kind of break the function apart as much as you can into 2 pieces. And then you're going to look at the 2 pieces that you have to work with. So to get started here, we have a fraction, 3x squared over x cubed plus 1. Let's break that fraction apart. And we're going to write that as 1 over x cubed plus 1 times 3x squared. Why can we do that? Just a little bit of algebra trickery. We know that if we have a fraction a over b, that's the same thing as really multiplication by the reciprocal. So it's the same thing as 1 over b times a. So instead of dividing by b, we're really just multiplying by its reciprocal. So 1 over x cubed plus 1 times 3x squared. You can always do that with a fraction. All right, but when we look at that now, it's a little bit easier now to see the 2 pieces of our function. So let's do our 2 pieces. Again, this isn't necessary. Maybe you just do this in your head. You don't have to necessarily write this out, but we're just getting started here. So let's write down our 2 pieces. We have 1 over x cubed plus 1, and we have 3x squared. And we just want to identify what we think is the more complicated piece. And, we have a fraction, so I would think that's the more complicated piece compared to 3x squared. So we have this fraction, 1 over something, and we're looking at that complicated piece now to identify what the inner function should be, what we should choose for u, and we're going to let u equal what's in the denominator. It's inside the fraction there. It's the inner function. So that's how we're going to choose u, is we've identified the complicated piece, and then we're looking for the inner function for that complicated piece. All right, so let's do it now. So we've chosen u. And let's write up our solution. So we're doing the integral of 1 over x cubed plus 1 times 3x squared. And you don't necessarily have to rewrite it like that, but I personally find that helps. And we're going to choose u now, and we said we're going to let u equal the complicated term that was in the denominator, so x cubed plus 1. Once we choose u, it's up to us then to calculate du, so we're going to differentiate. So derivative of x cubed plus 1 is 3x squared. And then we're going to multiply on dx. And that's step 1. Choose u, calculate du. Step 2 now is we want to kind of put all those pieces into our integral and get just an integral that's in terms of u. So let's look at what we have. We know from our choice of u here, wherever we see an x cubed plus 1, we're going to replace that with u. So if we look, well, right there is x cubed plus 1. So I'm going to replace that with u. And let's start writing this out. So instead of 1 over x cubed plus 1, if I make that replacement, if I make that substitution, I'm going to have 1 over u. So I go from 1 over x cubed plus 1 to 1 over u. Now, if we keep looking, we still have a 3x squared dx here. I have to get rid of those. I have to change those to u's in some way. And we have this other equation to work with. And it just so happens that we know exactly what 3x squared dx is. It's equal to du. So it's nice. It worked out exactly there. So we know that 3x squared dx is exactly equal to our new differential du. So let's make that substitution. So we put that in. It's now the integral of 1 over u du. And that's a nice one. So that's one. It's a whole bunch more simpler. It's a little easier than what we started with, the 1 over x cubed plus 1 times 3x squared. It's a lot easier to do the integral of 1 over u. So now let's actually do it. Step 3. Let's switch over and actually do the integration. And this is one of our basic integrals. We just have to have it memorized. Integral of 1 over u, natural log, absolute value u. So remember the absolute value there. And then as soon as we get the antiderivative, let's remember our arbitrary constant plus c. And yeah, we're done. We're finished with the integration. Now all that's left to do is get our antiderivative back to x. So right now it's in terms of u. We're so close, but we're not quite there. Step 4, let's get it back to x. So wherever I see a u in my antiderivative, I'm going to plug in back, I'm going to substitute back x cubed plus 1. So it'll be the natural log of the absolute value of x cubed plus 1. And then we have our plus c. And there we go. That's our antiderivative. All right. So that'll do it for today's lesson. In the next lesson, we're going to see what happens when, especially for these first 3 examples, it was just to kind of get us introduced to the process. But in the next lesson, we're going to see what happens when we don't get so lucky here. Right here. Everything was a nice perfect match. All the pieces fit in perfectly. What we're going to see next time is what happens if the pieces don't fit together so nicely. We're going to have to do a little bit of manipulation to kind of make them fit. All right, so we'll stop there for today's lesson. Enjoy the rest of your day, and we'll see everyone tomorrow. Bye-bye.